The simple fact that we're going to start with is that sine of anything is going to be less than or equal to 1. And it's going to be greater than or equal to negative 1. This is why we like to use a squeeze theorem with trig functions, because of this statement right here. And that can be a constant function, and that's a constant function. So you kind of have this thing going on. You have f of x is less than or equal to this upper function, x, or u, and it's greater than this lower function, L. My upper function is 1, and my lower function is negative 1. Because, okay, think about the graph of sine. You guys remember the graph of sine? Okay, the highest number is 1 and the lowest number is negative 1, right? And when I graph this, it would do something like this, and it keeps going forever. So this is the graph of sine, theta. So the function sine is never above 1, and it's never below negative 1. So we have a lower function and an upper function. My upper function is positive 1, and my lower function is negative 1. So I have y equals 1 and y equals negative 1. The sine function is always in between 1 and negative 1, right? Okay, so because we can start with that, we can go and attack crazy dudes like this. And what we're going to do is we're going to use manipulation for this. So here, check this out. Write this. We got sine of 1 over x. Okay, I know it says 1 over x, but that doesn't matter. It's just something inside of sine. Your result right here will always still be less than or equal to 1, greater than or equal to negative 1. Agreed? It doesn't matter what's inside of the sine. Sine will always produce a number that's between 1 and negative 1. All right? Now, what we're going to do is we're going to try to make this look like this. So what would I have to multiply this inside function to make it look like that? X. So if I multiply everything by x, it looks like is everybody cool with that? Because that makes sense now, right? So here's your in-between function, and there's your lower function, and there's your upper function. Now, do you guys know what these two functions look like? Because that's the neat part about the squeeze theorem is you don't care what the inside function is doing. You don't care what the inside function. You care about the outside functions. And so we have this function and this function. You guys know what those look like? Let's see. What is this written in slope-intercept form? Let's help you guys out. It would be y equals 1x plus 0, right? That's the same as y equals x, that function, right? So your y-intercept would be 0. Your slope is 1 over 1. You guys with me? So I put a dot right here at y equals 0. I go up 1, right 1, up 1, right 1, up 1, right 1. And I can go the other way, down 1, left 1, down 1, left 1, down 1, left 1. And I have this line right here. So this function right here is this. You guys with me? Yes. Okay. Now, is this function always going to be above this guy right here? I don't know. Maybe. And then we have this one right here. That would be down 1, left, down 1, right 1, down 1, right 1. And so you have this function right here. Do you think this function right here that's inside, that's in the middle, will always be above the negative x and always be below the positive x? I don't think so. Yeah, because this one goes down, and we know that sine functions oscillate, like it does this thing, right? So how can I make sure that this one is always above and this one's always low? And I don't think you'll ever have to do this on any other problem that you do in your homework. This is just a tricky one. You're like, okay, why are you doing it? What would my function look like if I did this? Teach my functions. This would make this one always above the x-axis. This one would always be below the x-axis. Can I take the absolute value of all these? Of this whole thing? Let's see. So how would that look? Would this function always be above and this function always be below? I'm warning you, this answer is not satisfying at all. Let's take the limit of the upper function and the lower function. So we have the limit as x approaches 0 of the absolute value of x. Can I do direct substitution on this one? Yeah, so plug into 0, what do you get? Okay, let's try that with the other one. What, if I plug 0 into that, do I get 0? Okay, so what would the limit as x approaches 0 be of x times sine?
0.
Yeah, this would equal 0. So that's how you use a squeeze theorem for this, but still, I know it's not satisfying. But we can look at this graphically to help us see it. So let's do that really quick. We know that if we plugged in 0 to this denominator right here, that it would be undefined, so we wouldn't be able to find this answer. But let's plug this into our graphing calculator to see what it looks like. Okay, so here's my function. When I hit graph, it does this funky thing right here. I kind of want to see what's going on there, so I'm going to zoom in, hit 2, then I hit enter. Yeah, there's weird stuff going on down there. Let's do a zoom again. Okay, so this is that crazy function that we're looking at. What would happen if we put the absolute value function on there? So I'm going to say math, and I'm going to go to, I need some abs here. I'm going to go 1, and then I put an x right here. What does that function look like on my graph? Oh look, it touches it right there, and it stays above the x-axis, or the function the whole time. Let's put in the other one. Get some abs again. Go math. Go over to num. And then we put a x in there. I'm going to have to put a negative out in front. I forgot to put that. So I'm going to press insert, hit negative. All right, now we have both our functions. Let's hit graph. So it looks like my lower function does stay below this the whole time. My upper function stays above this the whole time. Look what I got. Both of those squeeze the function right at the origin. So it helps us see the squeeze theorem right there.